The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody. Sorry for the delay there. Welcome to today's webinar on 5 ways to significantly reduce industrial energy usage. Paul Stiller is going to be giving this here in just a second. My name is Scott Ellis, and I'm with Onset Computer. And just to give you a rough overview of it, we are the world leader in we were founded in 1981, and we're located on Cape Cod, Massachusetts. We have roughly 120 employees. We do all of our manufacturing and design here from Cape Cod. We sold 1.5 million data loggers to date. A little bit about Paul Stiller. Director of Engineering for Summit Energy Services, subsidiary of Electric. He has 35 years of industrial energy management experience and has assisted hundreds of facilities in becoming energy efficient. He's also a certified energy management and we'd like to welcome Paul and have him take over from here. Welcome, Paul.
Thank you very much, and thank you to everyone for joining us today. We appreciate your time and hope that you find this presentation interesting and useful. I'm coming to you today from Cleveland, Ohio. So I'm with Summit Energy Services. My job is to help large energy users reduce their energy costs. We have a group that focuses on the price paid for gas and electricity, primarily procurement support, and then my group handles the demand side of the equation. So we focus on reducing energy usage. This isn't a commercial presentation, so I just have this one slide so that you have an idea who we are. We manage about $20 billion in energy spend, so that's the collective amount of money that our clients are spending on gas and electricity. We have a number of offices around the world in a number of countries and clients. I noticed myself with interest that we have 350 dedicated employees. We actually have about 410, so I think it's interesting that they make the distinction between the dedicated employees and the other 50 or 60, but I found that interesting. So we help clients using a collaborative approach that we call the Energy Consumption Workshop. This concept was pioneered about 10 years ago by a friend and colleague of mine named Thomas Mort, who might even be on the line today. It's a structured process that we use to help clients clearly understand their energy management problems before they consider a solution. A common mistake is to evaluate proposed solutions before anyone really understands the problem. So that workshop is the core of how we approach improving energy management with our clients. So we promised you to discuss 5 ways to significantly reduce energy usage. Here they are. Our goal is to get you thinking about the possibilities today. Most facilities can reduce energy 5 to 10% without significant capital expenditures. The key, as I said, is to understand the problems and then seek the best solutions. And in order to understand those problems, I recommend that you begin by collecting the facts, collecting data, and analyzing that information. Of course, there are many other opportunities, and I could go on for days, but we only have an hour. And so these are the topics that we selected. Some of them will be of interest to you, others perhaps are not directly applicable. In our overall workshop process, there are about 15 topics, and each one takes a day or so. This is just a sampling, again, to get everybody thinking about the possibilities. So the number one suggestion for reducing energy use, use the heat of compression. How many of you have an area that looks like this picture on the right? It's great for smokers that aren't allowed in the building. It's a nice warm spot near the building. But for an energy manager, this is an opportunity. What's actually happening here is warm air from an air compressor on the other side of the wall is being exhausted to the outside in the winter, creating this nice warm spot. You may be aware, or perhaps not, that air compressors are very inefficient. 75 to 80% of the energy that goes into an air compressor actually becomes waste heat. Very little actually ends up in the compressed air. So one of the opportunities is to make use of this waste heat. Signs that you may have that opportunity: if you're in an area that has a long heating season, or if you have significant heat requirements for your process, this would be an opportunity. If you buy a lot of fuel in the winter for heating the building, or if you have several large air compressors, that would be an indication that this is an opportunity for you. Now, a typical heat recovery system might look like this, where we bring outside air in across the air compressor, and then in the summertime we vent it back outside if we don't have a use for it. But in the winter, we vent it into the building. Now, there's a couple of advantages here. One is that the waste heat ends up in the building envelope, but the other is that the outside air is helping to pressurize the building. So if we have a situation where there is negative pressure in the building, and in the winter we're tending to suck cold air in through open dock doors and windows, in places where we don't want that cold air coming in, it impinges on workers, and then we end up installing heaters nearby. You can avoid that situation by pressurizing the building. So a heat recovery system like this has several benefits. Now, as I mentioned, the key is to get the facts. It's one thing to simply look at the compressor and make the observation that there's heat and we ought to use it. The question is exactly how much heat is there and what's it worth. So the recommendation is to get the facts and do the analysis. This is an example where we've used one of Onset's HOBO devices on each of 3 air compressors in my example in order to determine the average load in kilowatts and also the run time for a year. Now, we typically would not collect data for an entire year. We would collect it for a representative week or 2 and then estimate the running hours. But from this information and knowing that 75% of the input energy is waste heat, it allows us to calculate the value of that waste heat. In my example, it's $86,684 per year. Now, that's based on a cost for natural gas of $7.15. Your costs may be different, but my point here is that usually it's a significant amount of money. Now, in our analysis, we want to make sure that we accurately determine the value. So if the heat is to be used only in the winter, then we need to adjust for the number of winter hours. So in my example, if we're only going to use this heat for heating the building, it's worth about $46,000. Another interesting analysis that I recommend is quite simple. Take your gas bills each month and line them up for a year. If this were a factory, I would make the assumption that the gas usage through in the June, July, August time frame, in the northern hemisphere that would be the summer. If we assume that's the gas usage associated with the production facility, then we're interested in looking at the winter gas, the extra gas that is used in the wintertime for heating. This would give us an idea of the potential value of the heat recovery. So in my experience, when we're conducting workshops, we see about 100 to 150 facilities per year, and I would say on average that winter gas is anywhere from $10,000 to $100,000. I see on that slide we're missing a zero for the 100,000. We did get the comma in the right place. But this would be an interesting analysis that I would recommend for anyone that uses gas in production in order to get an idea how much of that gas is used for winter heat. So the second opportunity is uncovered by analyzing daily usage profiles. There's several aspects to consider, and the first is fixed usage. And this is really critical. If you look at how much energy you're using as a function of production. So these graphs show each dot would be 1 day or 1 shift, and each of those dots shows how much energy was used that day and how much production was accomplished. So if you take data for 1 or 2 years and construct such a graph, you'll see that a certain amount of energy is used at zero production. That's the fixed usage. Statistically, it doesn't matter whether we're doing anything in the factory or not, we're paying for that energy. Now, you'll never get it to zero. You have security lighting, you have computer networks, you perhaps have refrigerated product, or you have spaces that need to be conditioned all the time, you have security operations, so you'll never get it to zero, but you should have a feel for what your fixed usage is and how large compared to full production usage. Where this really shows up, we've seen it in the last couple of years, where a manufacturing facility, unfortunately because of economic conditions, is reducing the production level. If you have a large fixed usage and your production is reduced, you have to allocate the cost of that fixed usage to fewer and fewer parts of production. And so your energy per unit of production just skyrockets. And so that highlights the importance of understanding this fixed usage. Now, going after it and understanding it requires measurements. So as you understand the magnitude of your fixed usage, you're going to find that part of it is due to ventilation, lighting, air leaks, computer monitors, things like that. So as you understand how large your fixed usage is and begin to understand what you need to do to reduce it, making measurements around the facility with the temporary recorders is what we do, helps to understand the components of that fixed usage. This is just an example from one of our clients that was just looking at daily load data. This happens to be for a Sunday from midnight to midnight, where the load during the day is 6.5 to 7 megawatts, 7,000 kilowatts on Saturday, and then on Sunday, which is the second day shown there, it levels out at about 4 megawatts. So the top graph shows Saturday production load, 7 megawatts. Sunday is an idle day with a load of about 4 megawatts. So they started looking at this load data, scratching their heads and asking, what are we getting for our 4 megawatts on Sunday? got out their HOBOs and other equipment. They came in on Sunday, just started looking around, asking questions. What's running? Why is it running? And they were able to get the load down to 3 megawatts. So that's 1,000 kilowatts based on their energy rates, $73,000 a year saved, and that's with no capital expenditure. I know a number of our clients say, hey, Paul, great idea. We don't have any money to invest. There's just not much we can do about energy. I would say in my experience there's a lot you can do about energy even if capital is very tight, and that was one example. Here is more what we call demand interval data, just wiggly lines. It shows the load in a facility for an entire month. What it shows is the daily peaks and also the minimums at night, and it doesn't go down that much. But one thing you want to look at here is consistency. Does it go down to about the same level in the evening, or is there a lot of variation? And does it go down a different amount on the weekend than it does during the week? Now, this type of data doesn't give you many answers. It just provides the questions. So since these weekends are different, the weekend is different than during the week, we ask the question, do we expect that? Maybe. We say, yeah, there are maintenance activities that go on at night during the week. We understand that variation. It's perfectly normal. But maybe there's no good explanation other than more equipment is turned off over the weekend simply because the workers are in the habit of turning more things off, and in fact they could turn them off during the week. So the topic is fixed usage. That's the opportunity. Your challenge is to understand how large is your fixed usage and what are those components. You can guess, but it's typically not intuitive. You should take some meters out in the plant, leave them on different pieces of equipment for a day or two, then analyze that data and get a real feel for what are the contributors to your fixed load. And I believe you'll find that you can significantly reduce it. So I'm still on item 2. I called this 2B, managing demand. We're still looking at the wiggly lines, but the peak usage during the day can also be really important because you're probably paying a demand charge on your electric bill. In addition to paying for the energy, you're likely paying a demand charge. Now, we think in terms of load factor, and this slide shows the definition of load factor, which is the average load divided by the peak. So in the first graph on the top, we see a 19% load factor, relatively low, because the average usage is down around 150 kilowatts, but the peak is almost 700. If you could level that out, as we've shown in the second graph, load factor 79%, here the peak is not a whole lot higher than the average. And so in this case, even though we would pay the same for the energy, for the kilowatt hours, you'll save money on your electric bill on the demand charge by understanding when that peak occurs and making sure that only essential equipment is running at that time. So that's the action item for you around demand charges. You should know when the peak occurs and make sure that only essential equipment is running. So how do you do that? Well, maybe you have a permanent metering system, or perhaps your electric utility for a fee or maybe even for free will provide interval data like you see here. That will show you when your peaks occur. Now, you may need some portable devices to sort out exactly what is running during that time. what we see is there may be a batch process. Maybe you're grinding scrap or preparing certain materials for production, and it's not a continuous process, it's a batch, and it can be done at various times. You'd want to make sure if it uses a lot of power that you do that off-peak. I've seen some fairly dramatic examples where, for example, a paper operation where they repulp cardboard boxes, they could take cardboard boxes and make enough pulp to run the paper machines for an entire day. It only took them about 4 or 5 hours to make the pulp. They were in the habit of running these repulping machines during the day, which happened to be during a peak time. It was almost 1,000 horsepower worth of load. And just by moving that pulping operation to second shift is a very dramatic savings on their electric bill. If you don't have interval data, you should get it. Monthly data, if you have to wait till the end of the month to get it from your supplier, that's usually not fast enough. Because if you're trying to understand peaks, it may be very difficult to think back 3 or 4 weeks to identify what might have been running at that time. And so you really need access to data maybe the following day. We even use the HOBOs occasionally. If there's no other way to get it, we just take those little CTs up there, put them around the mains. You know, if you've got low voltage, if it's, you know, under 600 volts, that would be a viable option. We don't have to have kilowatts here. This isn't determining the bill. We just want to see the profiles. So even if you just look at the current profile, that is another way to get a feel for what your usage is. So here's my recommendation. You should know if you pay a demand charge. Some of you don't, and so this isn't an opportunity. You should know when your peak occurs and make sure that you've only got essential things running. Now, there are PLC-based control systems that will monitor your usage, and as you approach a peak, start shutting things off. I've never seen that really practical for a couple of reasons. Most production managers are not going to take kindly to some controller that can start shutting things off. It just doesn't make sense. But also, if you start opening circuit breakers automatically, logically you're going to shut off things like the parking lot lights and other things like that, which probably aren't on during the peak period anyway. So my recommendation is to start with a simple stack light like this and have a meter or a little controller that lights the green light when there is no possibility of setting a peak, light the yellow light as you're approaching a peak, and the red light when a peak in fact has been reached, and put 2 or 3 of those stack lights around the area so people can just be aware. When they see the yellow light, just think, is there something you could turn off? Are you getting ready to start some process that could wait 30 minutes or an hour? So that's my recommendation for a practical start. Now, number 5 is a common mistake that I see. Soft starting motors will not help. Some of you may think that, say we have a 500 horsepower motor, maybe it's a chiller or an air compressor or it's a blower or something associated with production. And it is true that if you start a large induction motor, particularly across the line, there's an enormous inrush current. That inrush current should not be confused with real power. There is not a surge in real power, and soft starting that motor will not help with demand management in any way. So I'm ready to move on to number 3, ventilate on demand. One of the easiest ways to reduce energy usage is to stop bringing in so much outside air. In the old days, we designed for a minimum CFM a minimum volumetric flow per person based on maximum occupancy in a facility. That doesn't apply to factories, and it's just not the best approach anywhere. Even if we think, for example, of a large office building, the reason you bring in outside air is because people convert oxygen to CO2. And you have to limit the CO2 levels. So if you put a whole bunch of people in a sealed space, the CO2 levels will rise to uncomfortable and eventually dangerous levels. And so you have to bring in outside air to keep the CO2 level below or in a safe range. So when we say ventilate on demand, what we mean is measure the CO2 level and bring in as much outside air as you have to keep the CO2 level in a safe range. Usually it's a certain, it's measured in parts per million, ppm, and usually the ambient is CO2 levels are 300 to 400, and you want to limit inside, say, to below 1,000 ppm. So you would bring in outside air to keep the CO2 level below 1,000 ppm. But now here's what happens. Maybe it's a Friday afternoon, not a lot of people showed up for work, or they're all out doing something, not that many people in the office. CO2 level starts to drop. The HVAC controls, or the ventilation controls, see that the CO2 levels are dropping, and they bring in less outside air. Now, who cares? Well, it turns out to make a huge difference. I just put one example here. If you bring in 100,000 CFM from outside, and it's 25 degrees colder outside than it is inside, if you do that all winter, and you're paying $9.50 a million BTUs for gas, that's 102,000 bucks, almost 103,000. So, as I said in the beginning of this discussion of number 3, this is a huge opportunity for many facilities. Now, my example is given for heating, but the exact same thing applies for cooling. If you live in an area where it's very hot and humid, you want to bring in as little of that air as you must, because it has to be cooled, it has to be dehumidified. Here's an example analysis. The ventilation is, we often think in terms of air changes per hour. So if you have a facility and have no idea what the air changes should be or what the CFM should be, this is a simple calculation that will help you. In this particular case, I have 3 different areas of a building. I have a molding area, a main plant, and a warehouse. I know the area of the floor in square feet and the average ceiling height. So I can calculate the volume enclosed by the building, and I use a factor of 80% because the building has other things in it besides the air. It has people and equipment. So we use a fill factor of 80. And in this particular example, I start with 4 air changes per hour, and that tells me that my ventilation requirement is 282,667 CFM. So that's a place to start. If you have no idea what your ventilating system is doing, get a quick calculation as to how many changes per hour you have. Now, there's no standard for the number of changes. The recommendation is, if it's a factory or an area where there's no concern about CO2 levels, then the best approach is to simply minimize the ventilation. You may have smoke or mist or other things that have to be taken out of the environment that will drive the ventilation requirement. In a space where it's dominated by people, if this is an office or a restaurant or a school, then you need to measure CO2 levels and implement the demand ventilation, where you have controls that are going to only bring in the amount of air that's required in order to maintain the CO2 levels. This is an example air balance. If you have a factory, just draw a square and figure out what's coming in and what's going out. You may have exhaust hoods, you may have air makeup units. This is a way to get a feel for where the air is coming in, going. So there's two important points here. The first is ventilate on demand. Only bring in the amount of outside air that you must to get the job done. But secondly, you want to bring the air in where you decide to bring it in. In other words, in this case, I'm ejecting a certain amount of air, a total of 100,000 CFM, but I'm only bringing in 80,000. So there's another 20,000 that's going to cause the building to become negative pressure and suck air in through the dock doors and other areas down low where you're not going to want it to come in. It's near people, and that's where you're going to require supplemental heating. So that's the recommendation around ventilation. My fourth item is dispatch compressors economically. We know that compressed air is a really inefficient way to deliver energy, and everybody knows they should be fixing leaks and avoiding air usage. But there's another aspect that you should consider. If you have more than one air compressor running at a time, it's really important to be sure the controls are working properly. In this particular case, I have 7 air compressors. So we showed up at this facility with 7 HOBOs, 7 CTs. We put 1 on each compressor. We let it run for a week. That gives us this diagram. Each color is a different compressor. There are a lot of things to learn from these diagrams, but the most important I'd like to point out is that several are modulating, trying to control pressure. They're working against each other. What you would expect to see here is all the machines that are running run at a base load at their most efficient point, and then one compressor that's good at partial load modulates in order to maintain the pressure in the system. So in this particular case, we can see the controls are not working properly, and we have more than one machine loading and unloading. Now, the reason this is important is that that's an inefficient way to supply the air. You could, if you fix the controls on these air compressors, you could reduce the cost of producing that air. This is just a reminder that there are a number of ways to control air compressors. Somebody needs to modulate. You can't just let all the air compressors run at their most efficient point. Then there would be no pressure control. So we have to have one machine that's changing its output in order to maintain the pressure set point. Now, the most efficient way to do that is with a variable speed air compressor. You can see on this diagram that the magenta line, the small, I think that's magenta, the almost straight line between the 100%, it shows that it uses 100% of power for 100% output. But as you reduce the compressor capacity down to 10% or down to 0, it's only using a few percent of its output. If you contrast that with a modulating air compressor, where we're just closing off the air passage in order to reduce its output, that works fine. It will reduce its output and hold pressure on the system. But what you may not realize is, now this is the red line, even when that compressor is only running at half its capacity, it's using 85% of its rated power. And even when it's fully unloaded, it's not doing you any good at all. It's on standby, it's ready to go, but it's not putting out any energy. It could be using 70% of its rated power. So you should make sure, if you have more than one air compressor, that the controls are set up properly so that only one is modulating, and ideally you want the machine that's modulating to be one that's really good at it, perhaps a variable speed machine. This is just another example using HOBO data that shows two air compressors. They are working. These are controlling the way we would hope. One is sort of base loaded, and then the other one loads and unloads. But we should be aware that loading and unloading is not very efficient. In this particular case, the second air compressor, the one with the blue line, has an output of 114 CFM. So if we could reduce our air usage by 114 CFM, that machine would not need to operate. Now, based on the HOBO data analysis, we know it costs $17,000 per year to operate that machine. And so the potential savings, if we could reduce our usage by 114 CFM, is $17,000. And it turns out it's not that hard. Those of you that have seen leak tables, you may be able to go out and just fill 4 or 5 leaks, and that second machine would shut off. Just one more example around compressed air. This is a printing operation where large stacks of board, of heavy paper, move along an air table here. And these are little ball bearings that close off the airstream, and when the stack of paper rolls by, the balls are depressed slightly and opens up a passage for air to float the stack of paper. So I noticed in one of my visits that one of the balls was missing. So what? The operators get used to hearing that hissing sound. It just becomes the sound of doing business, not realizing that $5,000 worth of air passes through that one hole every year. We're ready to move on to number 5, manage boiler performance. Now, when you ask about boiler performance, many of my clients show me a strip of paper that it almost looks like a cash register receipt that says they're running 83% efficient and they have a tune-up every year. Well, but that's not the whole story. That piece of paper that comes from your tune-up guy shows the combustion efficiency. And it's pretty accurate for the combustion efficiency, but there are other losses, and they're mostly fixed. For a boiler, the biggest losses aside from combustion are going to be radiation losses. It's a large, hot piece of metal that's radiating heat to the environment. And that's a fixed loss. In other words, since the boiler temperatures and pressures are about the same, no matter what the boiler load, you're going to lose that amount of air, or the amount of air, you're going to lose that amount of heat, no matter what the boiler load is. So if you've got a strip of paper that says your efficiency is 80-something%, be careful. That's not the whole story. And if you're running that boiler at partial load, your efficiency is probably a lot lower than you think it is. My recommendation, monitor the evaporation rate. How many pounds of steam did you get per pound of fuel? And target that. Figure it out once a month, set a goal, and make sure you're managing to that level. Now, easier said than done. We don't know what our steam flow is. We don't have a steam flow meter. That's not unusual. Most boilers do not have steam flow meters. Fortunately, my friends at Onset have a little gadget. What you can do is just put a runtime recorder on the boiler feed pump, and you can assume a flow rate. If you just know the runtime on the boiler feed pump, that'll give you a pretty good idea of the pounds of feed water that eventually convert to pounds of steam. Surely you have a meter on the fuel. You're buying it probably, and so you typically have a measurement on the fuel. A simple runtime on the boiler feed pump could get you the data that you need to monitor that evaporation rate. If it's a hot water boiler, you're not evaporating at all. You may need a BTU meter, which is just a fancy way of saying we're going to measure water flow and we're going to measure temperature difference, temperature in and temperature out, and use that to calculate the BTUs. So those are the 5 ways to significantly reduce energy. I say they're not these are 5 ways. They're not necessarily the 5 ways. There's hundreds of others. I do have a few more thoughts to share, so I would invite everyone to stay on the line. There's a couple other things. We have a few minutes that I'd like to share with you. Number 6, this is really important. It's a business process that you can use to be much more effective in energy management. Here's the thing. Everybody's got solutions, right? Everybody's out selling solutions. And so my question is, do we understand the problem? What exactly are we trying to solve? The recommendation is use a problem-solving method. Look at situations, understand what the causes and effects are, look at different alternatives, and then implement the best solution. That process will lead you to much more effective energy management. Just a quick example. Let's say the problem is I'm a food plant and I've got condensate dripping off the ceiling. That's going to shut you down. Somebody says, well, I think the issue is these dampers. They're closed. We need some more outside air. Somebody jams a 2x4 in the dampers. Condensate goes away. Problem solved, right? Well, not really. Jamming those dampers open has made a temporary alteration to the control system. Maybe there's a better long-term solution. So I'm not saying that those floor mechanics shouldn't go jam that board in if it helps us get the line back up and running. They should still do that. But somebody should report that temporary alteration so that the control of the air handlers and ventilation and control of condensate in the plant can be carefully understood so we can see, well, you know what, let's go change the program in this PLC, or let's put a fan over here, and let's go take that 2x4 out of the dampers. If you don't get control of that, what happens is you go implement different energy conservation measures, you see a reduction in energy, but then in subsequent years it creeps right back up again. Because all those floor mechanics are out there doing their best and doing their job, but nobody's following up to really understand what the impact is of their actions. This is just a specific example. I went to a facility and looked at the log for what the maintenance floor mechanics were doing. And these were a variety of modifications that had been made. Somebody calls from production and says, you know, our label machine is jamming. We turned up the air pressure and that seemed to solve it. We needed to check some things, so we added some more light. Then somebody calls on June 16th and says there's some containers. This is a food product container that's hanging up around a corner, so we add an air line and we blow on it. Somebody called on July 15th. This was my ceiling condensate example. There's a slick floor problem. We got water on the floor on August 10th. We put an air hose on it. So all these actions taken solved the problem, right? Well, yes and no. If you go back to these items and look at the resulting cost in energy use for a year, you find out that this one floor mechanic increased operating costs by $33,625 per year. Holy smokes. You say, we could, you know, how much approvals would be required in your company if you wanted to hire another floor mechanic and pay him 30 grand a year? A lot. And you probably wouldn't get approvals anyway, right? It's hard to get additional headcount. This particular mechanic made all these changes. He didn't need any approvals at all. Just go out and do it. So that's my suggestion for item number 6. I'm not saying that those mechanics aren't doing their job. They are, and they're doing it very well, but they need backup. They need somebody the next morning to look at the mechanic's log and say, oh, I see we overrode this air handler control last night. We need to go understand that problem and see if there's a better way to fix it. So using problem-solving methodology is my recommendation. So I think we have time for one more. I hope you all can stay on the line for another 10 minutes or so. We're scheduled for an hour. This is something that I think is pretty important. I know it's frustrating for a lot of clients. The subject is reactive power. You know, they remember from high school science class about simple electric circuits with batteries and light bulbs, and they remember Ohm's law of volts equals amps times resistance, power, volts times amps, and then they get their electric bill and it says, you know, reactive demand charge or reactive power charge. And it's like, what? And then you call your local power company and they say, well, that's the imaginary power. Just imagine the square root of -1, and and you're like, what are we talking about here? So I'd like to just give you my sort of my explanation here, because it's very important to understand how much reactive power your facility uses and what you're paying for it. And it's also important to understand the difference between real power and reactive power. There are a lot of vendors out there selling solutions, quote unquote, that exploit the fact that many people do not understand clearly the difference between real and reactive power. So, two things are different from that high school science class. First of all, the power source is not a battery, it's an AC generator. So I've got 50 hertz or 60 hertz alternating current. And the other thing that's different is light bulbs are resistive loads. In commercial and industrial facilities, a lot of motors are involved, and those are inductors. Those are inductive loads. So there's actually two types of power. The real power is what produces shaft torque and speed in the motor. That's what produces heat in a heater. That's what produces light, useful work. And for motors, the real power is shaft torque and speed. If you wanted to supply your own real power, then you would need a water wheel or a generator, a diesel generator, some type of prime mover in order to supply your own real power. But now, the other power is called reactive, and what's happening is it's energy that's in the inductor, the inductance part of the motor, for a half a cycle. For the other half of the cycle, your supplier's holding it for you. Then they give it back to you, then it goes back to them. If you have a 60 hertz power system, then that reactive power is actually bouncing back and forth 120 times a second. It's in the inductor for half a cycle, out to the supplier, and back and forth. Now, you can measure both of these components, and I see here that our friends at Onset have some products available to you that would make a simple measurement of the real power and the reactive power. The way we draw this in a diagram is called a power triangle. So most of us are familiar with the real power, which we measure in kilowatts, and the reactive power is measured in units of volt-ampere reactive, or VARs, and usually we're talking about thousands of VARs or kVAR. So I have real power in kilowatts, I have reactive power in kilovars, and then if I connect the diagonal, that's what's called apparent power, and the units are volt-amperes, or kVA. Now the reason that's called apparent power is, if you remember from high school that power is volts times amps, even on an AC power system, if you multiply volts times amps, you'll get power. You'll get apparent power. So it's important to remember that the apparent power is actually made up of two types, the real and the reactive. Some of you may have heard the term power factor, and that's just the ratio of real power to apparent power. So if we had no motors and no inductive load, if we had only light bulbs and resistive load, you might imagine that this triangle would just be a straight horizontal line. There would be no reactive power, no kVAR. So the real power and the apparent power would be equal. And that's a power factor of 100% or a power factor of 1, or sometimes, to be fancy, we call that unity power factor. As you require more reactive power, the power factor will go down because that ratio of real to apparent will go down. So, important question, how much reactive power are you buying from your utility? Because remember, if envision first in the lower diagram here, if the reactive power is bouncing between the inductor to the utility and back, if you're asking them to hold it for you on those other half cycles, it's passing through the revenue meter, they may be charging you for that. Maybe not. It's like demand charge. Everybody's different. You have to look at your electric bill, call your utility, ask them to explain it to you. Maybe, even though they're holding that reactive power for you every on the half cycle, there's no charge for it. Or maybe it's a very small charge. But maybe it's a really big charge. So here's the good news. If you want to generate your own real power, you have to have a prime mover. If you want to generate your own reactive power, all you need is a capacitor. When we say that the utility is holding that energy for you every half cycle, what we really mean is they have capacitors that are holding it. If you put a capacitor on your side of the meter, you can't change physics. The reactive power is still, or the reactive energy is still going to bounce between the inductor and the capacitor, but they're both inside your facility. The revenue meter never sees it. So if you're paying a lot for reactive power, you should consider installing a capacitor bank. Now these are typically called power factor correction capacitors, and hopefully you can see now why that would be the case. From the viewpoint of the meter, when the capacitors are there, it looks like the power factor went way up because very little, if any, of that reactive energy is passing through the meter. Now it is true that there's a small additional savings associated with putting in your own capacitors. My recommendation is to ignore that if you're considering investing in power factor correction capacitors. Only buy them if they can be justified based on eliminating the penalties on your electric bill. I would not place a significant value on savings associated with line losses and other things. You may see material available from vendors indicating additional savings from capacitors. I would say that's icing on the cake, and that you should not use that to justify the investment. So we're getting close to the allotted time here. These are the 7 topics that we discussed. We're not set up to take live questions here from such a large audience, but here's some contact information. You'll soon be able to find links on the Onset website for a recording of this material. And again, we thank you for your time. We hope you find this information useful in your efforts to become more energy efficient. And so we may have some final comments from the Onset folks, or we will, for the next couple of minutes, leave this contact slide up so that you can make notes on how you might reach us. Thank you very much.
Yeah, thank you, Paul. We appreciate it. And again, if anybody has any questions whatsoever, feel free to give us a buzz, and there will be an email follow-up which will have a link to this live presentation. So thank you again for joining us, and have a great day.